Hello there. Today we will continue with the series of ODE of first order. And in this episode, I want to talk about separable ODE. Because separable ODE yields many useful physical models. So I want to highlight the importance of modeling by introducing 4 examples of physical problems and their modeling. A separable ODE is called as such when the variables x and y can be separated in an ODE in the process of solving y, just like equation 3 as an example. All the y terms on the left side and all the x terms on the right side. Let's take a look at equation 0. Function f of x, y, and y prime equals 0 is a general form of ODE that we encounter in the real world. When I say general, it means that function f equals 0 might contain some more complicated terms than x terms and y terms, such as the product between x terms and the y terms, or the product between x terms and y prime. On the other hand, equation 1 looks simpler because all the x terms on the right side and all the y terms on the left side, except dx as the denominator of y prime. So, the form of equation 0, which is a more general form of ODE, is more diverse than the form of equation 1. But somehow, if you rearrange the equation 0 and successfully reduce it to the form of equation 1, then equation 1 is a good start. This is a good start where you can take integral of both sides of equation 1 to eliminate y prime and ultimately solve y. Please be noted that y prime has dx as the denominator, so both dx on the left side of equation 2 can be crossed out. Then we get equation 3. All the y terms on the left side and all the x terms on the right side, proving that equation 1 is a separable ODE. Of course, the integrals only exist if f and g are continuous. If this premise holds, then we can solve y. Now we will discuss a modeling example, which is to use radiocarbon dating to estimate when did a mummy approximately die. In this specific example, it says when did a mummy approximately die if the ratio of carbon 14 to carbon 12 in this mummy is 52.5% of that of a living organism. First, let's see the ratio of carbon 14 to carbon 12 is denoted as y0, and y0 is constant for a living organism. And after this living organism died, it stops eating and breathing. In a word, it stops absorbing carbon 14 from the environment, so carbon 14 starts to decay. And this radioactive decay is governed by this ODE, y prime equals k times y, which means that the time rate of change of y is proportional to the y itself, And as per what we have learned from last episode, we know that the solution y equals y0 times the exponential constant to the power of k times t. And this y0 is this constant ratio is considered as the initial value of this exponential decay function. And also we can predict that k is a negative number. And what's in the middle is the detailed calculation, which we want to overlook for the moment. And additionally, it says half-life of carbon-14 is 5,715 years, which means that the radioactive carbon ratio y of t will decay to half of its initial values after 5,715 years. And up to this point, we can foresee that we can substitute this condition into this function to get the k value. Now we really substitute this condition into the y, the radioactive carbon ratio, as a function with respect to time. T is the half-life of carbon-14, and k is unknown, and 0.5 is the value to which the radioactive carbon ratio decay after this so many years. So we get the k value. And then, as per the question, now k is known, and we want to know t, how many years for this value 0.525 to which the radioactive carbon ratio decay. So finally we get t equals 5,312 years. Now we move on to the second modeling example. This is a mixing problem. This tank contains 1,000 gallons of water, in which initially 100 pounds of salt is dissolved. Brine runs in at a rate of 10 gallons per minute, just like here it shows a pump and a section of pipeline through which the brine flows into the tank. And each gallon contains 5 pounds of dissolved salt. The mixture in the tank is kept uniform by stirring. Brine runs out at 10 gallons per minute, just like here it shows a section of pipelines through which the water flows out of the tank. Find the amount of salt in the tank at any time t. So this can be denoted as y of t. And by the way, the time rate of change of y of t can be denoted as y prime of t. The goal is to find y of t, but as per the information given, we cannot do that with the help of y prime of t. So we need to find the relationship between y of t and the y prime of t, which is the ODE. Here it says y prime of t equals salt inflow rate minus salt outflow rate. This is the starting point for for our physical modeling. If you cannot understand this, it will be difficult for us to move on. So let me give you some little explanation. A y prime of t is the variation of the amount of salt within an infinitesimally small time interval. And salt inflow rate represents the amount of salt being added into the tank as per unit time. And salt outflow rate represents the amount of salt being taken out of the tank as per unit time. Here we try to plug real numbers in this description, and we write down the physical unit for each number. So you can check the calculation by comparing the physical unit between these two terms. You can see that both gallons can be crossed out, so the physical unit for this term is pound per minute, which is the same with that of this one. And also we can compare the this physical unit pound per minute to this description, and we can see that because pound per minute is the mass flow rate, so it aligns with the definition of salt inflow rate and salt outflow rate. So finally, we get our ODE. Y prime of t equals 50 minus 0.01 times y of t. So we got the ODE as shown here. So let's move on to solve y. With some proper arrangement, we can make this ODE into this one. And this one is what we call a separable ODE, because all the y terms on the left side and all the t terms on the right side. And not only it is separable, but also it seems solvable. So after calculation, which we want to overlook for the moment, we get y equals 5,000 plus c times the exponential constant to the power of minus 0.01 t. And you can notice that there is an exponential decay function here. Actually, without the calculation, just by looking at this ODE, we can predict that there will be an exponential decay function in the solution in advance, because you see this is y prime, this is a constant which is negative, and this is y itself. So y prime equals a negative constant times y itself is tells us that there will be an exponential decay function. This is what we have learned from the first episode, right? So now C is unknown. In order to solve C, we want to plot the initial condition into Y. So the initial condition tells us that initially, which means when time equals 0, the Y, which is the amount of salt in the tank, equals 100 pounds. So after substituting, we get C, which is 4,900. So we get y of t like this. So finally, we got the y of t, and this is the ODE in a separable form, and here it says this function shows an exponential approach to the limit 5,000 pounds. Can you explain physically that y of t should increase with time? The exponential approach means that because y of t contains an exponential decay constant, and the value of y of t will approach the limit of 5,000 pounds as time increases. This is why we call it an exponential approach. And he asks, can you explain physically that y of t should increase with time? Since it says physically, so we have to go back to the illustration of the tank. That is where the physical problem is. So according to the question, the tank contains 1,000 gallons of water in which initially 100 pounds of salt is dissolved. So we can calculate that the concentration of the water in the tank initially is 0.1 pound per gallon. And the brine, the inflow of brine, the concentration is 5 pounds per gallon, right? So the inflow of brine is of high concentration, and the water in the tank is of low concentration. And secondly, because the volumetric flow rate of the inflow and the outflow are identical, so the total volume of water in the tank will remain the same. And if the inflow and the outflow goes on, you can see that ultimately all the water in the tank will be replaced with the high concentration brine. So when that time comes, all the water in the tank will become the brine, so the concentration of the water will be the same with the brine, which is 5 pounds per gallon. And when you times this concentration by 1,000 gallons, it becomes 5,000 pounds of salt. So yes, physically, you can predict that the end value is 5,000 pounds. At last, it asks, can you see the limit directly from the ODE? Oh, that's even easier, right? Because this is an exponential decay term. So as the time approach infinity, this term will approaches to 0. So the y of t will approach 5,000. Let's move on to the third modeling example. That is heating an office building. The daytime temperature in an office building is maintained at 70 degrees Fahrenheit. The heater is shut off at 10 p.m. and turned on again at 6 a.m. On a certain day, the temperature inside the building at 2 a.m. was found to be 65 degrees Fahrenheit. The outside temperature was 50 degrees Fahrenheit at 10 p.m. and had dropped to 40 degrees Fahrenheit by 6 a.m. What was the temperature inside the building when the heating was turned back on at 6 a.m.? And here is some useful physical information. The rate of change of the temperature T of a body, which is this one, is proportional to the difference between T, this one, and the temperature TA, this one. TA is the temperature of the surrounding medium, and K represents that the rate of change of temperature T is proportional to the difference between T and TA. So up to this point, seems that we already successfully deduced a mathematical model to translate the physical situation. But here, the textbook tells us that this mathematical model doesn't necessarily fit the reality for all the time, because this kind of law is derived under assumptions that rarely hold exactly. So we still need to compare the calculation to the measurements that we take, which means that we really need to take measurements in this office building. So that is what we say, setting up a model and knowing its limitation. So given this ODE, we're going to solve T. But before that, let's take a look at TA. According to the question, we know that TA equals 50 degrees Fahrenheit at 10 p.m. and equals 40 degrees Fahrenheit at 6 a.m. So we got these two conditions, which are supposedly to be plugged into the ODE. Plugged into the T of T function. If the TA, which is the temperature of the surrounding medium, decreases at a steady rate, we can postulate that the function of TA is a line function, which is shown here. But we can foresee that if we substitute this TA as a line function into the ODE, the ODE will become too complicated. So the textbook told us that we can set TA to 45 degrees Fahrenheit, which is the average number between 40 and 50, without sacrificing too much accuracy. So here I say, okay, give me a break by setting TA equals 45 degrees Fahrenheit. So now TA becomes a constant. So obviously it will drastically simplify this ODE, because again we see the T prime, we see we see K as a constant and see T, so we can predict that there will be a exponential function in the solution. So after some arrangement, we can arrange the ODE into this. Again, this is a separable form, T on the left side and small t on the right side. And we can solve T function equals 45 plus C times the exponential constant to the power of kt. Obviously, there are two unknown constants in the ODE, and we are going to solve them. And please be noted that this is T, not TA. T is the temperature in the office building. So with this condition, 70 degrees Fahrenheit at T equals 0, we can predict that the exponential function term will be becomes 1, and so we can solve C. So again, we skip the detailed calculation. We get C equals 25. So now only K is left to be solved. Okay, so now we are going to substitute another condition into the T function. Remember that C is 25, and the condition we're gonna plug into the T function is where temperature equals 70 degrees Fahrenheit at 2 a.m., which is 4 hours after 10 p.m. So we plug T equals 4 into the function, so we get K equals minus 0.056. So we get T function like this. And finally, we're going to answer to the question, which is what will the temperature in the office building be at 6 a.m., which is 8 hours after 10 p.m. So we plug T equals 8 into the T function, so we can get the temperature equals 61 degrees Fahrenheit. As simple as that. So finally, this is our last modeling example. This is a leaking tank, this one. And also there is an outflow of water through a hole, which is at the bottom of the tank here. And the Torricelli's law shall apply, which we will introduce to you later. So it says this is another prototype engineering problem that leads to an ODE. It concerns the outflow of water from a cylindrical tank with a hole at the bottom. So there's a hole at the bottom. The initial height of the water is 2.25 meters. So this is the initial height. Find the height of the water in the tank at any time if the hole has a diameter 1 centimeter. So this hole, the diameter of this hole on the bottom of the tank is 1 centimeter. And when will the tank be empty? Which says that when will this height of water be 0? And here physical information is given. Under the influence of gravity, Torricelli's law dictates that Vt, which is the outflowing velocity of water, equals 0.6 times the square root of 2 times g times h of t. Again, this is the Torricelli's law, which depicts the relationship between the velocity Vt and the water level h of t. So now we want to set up the model. First, we start with the idea that the water volume flowing out of the tank is equal to the water volume diminishing within the tank. That sounds quite logical, right? So let's take a look at the former one. Delta V, which is the variation of water volume, equals to A times the velocity times delta T, and A is the area of the hole, and delta V star is the water volume diminishing within the tank, which is equal to minus B times delta H. B is the cross-sectional area of the tank, and H is the variation of water level. So by equating delta V and delta V star, we can get this expression. And now let's stop here and take a look at this expression to see whether there will be something we want, such as h of t and h prime of t. First, we notice that there are delta t and delta t and delta h, which means that we can get h prime when delta t approaches 0, right? And also we notice that there is velocity v, and by the Torricelli's law, we can get the term h of t into this expression. So this seems very promising to get what we want. So earlier, by equating delta V and delta V star, we get this impression, which seems very promising to get the h of t and h prime of t. So let's try. As delta t approaches 0, we have dt over dh of dt, dh over dt equals minus a over b times the velocity, and the velocity equals this expression, which is dictated by Torricelli's law. And both a and b are constant, and the g, which represent the gravity, is also a constant. So this ODE can be further arranged into this one, and we can notice that this is a separable ODE, and it seems solvable, right? So we get our ODE without further diving into the detailed calculation, because we want to downplay the importance of calculation and pay more attention to the explanation of modeling and interpretation. In this episode, I have introduced and explained 4 physical problems. Especially, I focused on the process of deriving a mathematical model from a given physical problem. In the next episode, I will explain how I perceive and make use of some calculation skills of ODE without diving into the details. So please subscribe to my YouTube and Facebook. Thank you very much. See you next time.